Okay, this is UBC Math 100, Past Final Exam 2014, question number 7. It says a particle 1 moves on the y-axis starting at the point 0, 6 and travels towards the origin with constant speed of 2 units per second. Particle 2 moves on the x-axis starting at the origin and travels in the positive x direction with constant speed of 1 unit per second. The first part here it says to write a formula for the distance between these particles as a function of time. And then next we're going to figure out at what moment in the first 3 seconds is the distance minimized. Okay, so first thing you should notice as a whole is that this is a optimization problem. We're trying to eventually minimize the distance between these two particles. And part A is kind of the setup because it will give us the formula for the distance. It'll give us the function that we are actually trying to minimize. Okay. The first thing we want to do is sketch out the situation. Okay. So the first particle starts on the y-axis, and it actually starts at 0, 6. So let's say here's the x-axis, let's say, and here's like 2, 4, 6. And so it's starting out over here. And it moves towards the origin with a speed of 2 units per second. So as it goes along, it's going along like this, going down like this, okay, over time. Particle 2 moves on the x-axis starting at the origin. So it's starting here. And it travels in the positive x direction. That's to the right, right? Here's x, positive x, with a constant speed. So if this is going, certain speed, this is going a bit slower. So maybe I'll make its arrow a bit smaller. Let's say like that. Okay. Now we want to find a formula for the distance between the particles. Okay, that means, for example, this distance between here and here. And this distance is changing over time as it goes more here. And this particle goes like this. It might go like this, or earlier on it might be like this. The distance is changing, and we want to figure out a formula for that as a function of time. Well, what formula do we use? Well, you might remember the distance formula between 2 points in the plane, which looks like this, right? Maybe I'll just remind you here. The distance between 2 points, it kind of comes from the Pythagorean theorem. You take the difference in the x values, you square it. The difference in the y values, you square it. And then you take the square root. Yeah? Square root. It's like the Pythagorean theorem. It's like a right triangle. So what we want to do is we want to find a formula for the x coordinate and the y coordinate for these 2 points as a function of time over time. Okay, let's start with the first particle. It's up here, and it starts out at 6. Okay. Well, you might notice that the x coordinate is always 0 for this first point, because it is always on the y-axis. So all we need to really know is what is the y coordinate. And the y coordinate starts at 6, and it decreases by 2 units per second. So we're going to write -2t to represent a rate of change of -2 per unit time. So this is our point. Now for x, it's kind of the reverse, right? Because x, its y coordinate is always 0, but its x coordinate is increasing. And here it starts at 0, and it increases by 1 each time because it has a constant speed of 1 unit per second. So that means it's going to be like 1t plus 0. In other words, just t. After 1 second, it'll be 1 unit across. After 2 seconds, it'll be 2 units, and so on. Whereas for this one, after 0, it starts at 6. After 1, it'll be down at 4, then down at 2, and 0, and so on. Okay, so this is what we have. So now let's apply this formula, and we're going to have distance, the square root. We subtract the 2x coordinate. That's just t minus 0, or just t squared. Then we have the difference between the y coordinates. So this minus this squared. Again, minusing 0 doesn't really do anything, so we just get this squared. And we take the square root of it. Okay, so this is the formula. The formula for the distance between the particles is a function of time. If t is time, then the distance, this d represents the distance between the 2 particles. Okay, very nice. Now let's go to part D. Part B, which says to figure out when in the first 3 seconds is the distance minimized. So we want to minimize distance. And to do that, we're going to find critical points. To do that, we're going to take the derivative, set it equal to 0, solve for t, find the critical points, and so on. You might remember that when you're minimizing a distance function, it happens to be easier if you minimize instead the square of the distance, what we could call d squared, because the distance is non-negative. It's always positive or 0. So in that case, minimizing the square and minimizing the distance itself is going to be equivalent. But minimizing the square is going to be a bit more convenient in terms of the algebra involved in terms of solving. So that's sort of a shortcut. If you wanted to, you could minimize the distance itself, do all the same steps, you get the same answer. Okay, I'm going to call distance squared capital D just for notation and simplicity. Okay, we want to figure out where is this minimized. So we're going to take its derivative. In other words, find d capital D over dt. Okay, what's the derivative of this? Well, okay, derivative of t squared is 2t. Then for this, I bring the 2 in the front, copy it down, and by the chain rule, I need to multiply by -2 as well. Okay. So if we want to figure out when this is 0, and if you simplify the left-hand side, you can see we're going to get 2 times -2, that's -4, times 6 is -24, -4 times -2t is plus 8t. So I end up with 10t minus 24. Collecting these together, and that's equal to 0. Okay, now to find the critical points, we solve for t. Okay, so I'm going to move the 24 over. And we get 24 over 10, which simplifies down to 12 over 5. So this is our critical point. Now, you might be thinking, well, what does that have to do with the first moment in the first 3 seconds? What does the first 3 seconds have to do anything? And it turns out, practically speaking, it doesn't really matter much. But notice that after 3 seconds, the second particle has already moved to the origin. It's already going down like this. So then things get a bit weird because now the triangle's sort of upside down. So that they're just trying to basically make the problem simple by including that restriction. It turns out even if they didn't have that, it would kind of the answer would be pretty much the same. Okay. But notice that 12 over 5 as a decimal, if you don't have a calculator, as a decimal, right? Oh, 10 over 5 would be 2. And so this would be 2.4. So it is within the first 3 seconds, this critical point. Okay. Now we have reason to believe that this is going to be where the minimum is. Because typically with these kinds of questions, if there's only one critical point, that will be the point where the minimum or maximum is. Now, to double check that, here's what we can do. There's a few different ways. One of them is to think, okay, we have a closed interval from 0 to 3. On this interval, we want to figure out the absolute minimum. And to do that, it can either occur at one of the endpoints or at one of the critical points. So what we could do is test t equals 0, t equals 3, and t equals 12 divided by 5. And then you can compute the distance squared in each case, right? It's t squared plus 6 minus 2t squared. So t squared is 0 squared, 6 minus 2c. I get 6 squared, which is 36. And for this one, I'm going to get 3 squared plus 6 minus 2t. So that's 0, and so this would be 9. And the question is 12 over 5 actually smaller when I plug it in? Will it produce a d that's actually smaller than these two? Now, if you plug it in directly, you're going to get 12 over 5 squared plus 6 minus 2 times 12 over 5 squared. And the question is this less than 9, essentially, because 9 is the smaller of these two? It turns out yes, but now you're going to have to do a bunch of fraction arithmetic here, right? So if I square this, I get this. And 6 is going to be 24 over 5. And it's going to be 20, no, sorry, it's going to be 6, it's 30 over 5, and this is 24 over 5. So when I subtract them, I end up getting 6 over 5. And then I'm going to square that. So I'm going to have 6 over 5 squared. All of this is if you don't have a calculator, right? Because on this exam, you don't have a calculator. And so in the end, you're going to get 144 plus 36, which is actually 180 over 25. And again, is this less than 9? Well, it turns out, simplify it a bit, divide both of these by 5. Again, this is actually tricky without a calculator. You get 36 over 5. Again, is that less than 9? Well, 35 over 5 would be 7. So it's just a bit bigger than 7. So indeed, this is true. And therefore, t equals 12 over 5 is the minimum. Now, this is sort of the brute force way. This is kind of the standard way. If you have a closed interval and you're trying to find the absolute extremum, so max or min, you test all the points. There is a little bit of a shortcut, which is to consider the second derivative, which is, we could write like this. What is the second derivative? Well, the first derivative, if you remember, is 10t minus 24 after all the simplification is done. In other words, the second derivative is just 10, which is in particular positive. It's kind of like the second derivative test. We are looking at the second derivative to see if it's concave up or down. Because it's concave up, because it's positive, that tells us that this t value is a minimum. Okay. Now, it turns out, if you have a function, and it doesn't really matter where the points are, it could be like here or here, and there is a minimum, right? The second derivative test only helps you with local minimum. So how do we know it's an absolute minimum over this interval? Well, if there's only one local minimum and it's concave up, it must look like this, right? Even if it looks like this, right? That one critical point is going to be the absolute minimum. Okay? So just from the second derivative test, we can actually conclude something about absolute minimum, not just local minimum in this case. And that's another way to figure out, to sort of confirm that it is. Once again, with these problems, typically the point that you're going to find is going to be the absolute minimum or maximum in another question. It's just about, if you want to show your work, you need to justify it. And this is some of the ways to do it. Okay, very nice. Let's just recap things. So first off, we use a little bit of algebra and to figure out what the coordinates of the point should be. And that would allow us to find the distance between them using the distance formula. Okay. Then we try to minimize this function. And to do that, a sort of a shortcut was to minimize the square of the distance. To do that, we wanted to find the critical points, and we found one critical point. We tested it out. You can either do it the long way, which requires some fraction work, or you can confirm it's a absolute minimum using the second derivative test. Because the second derivative is positive, therefore it is a minimum. And in this case, it actually is an absolute minimum. Okay, very nice. So that's all for this question. If you found this helpful, and you're interested in a full guide for this entire past exam, as well as other past exams, then check out my solution guide at the link below this video. Step-by-step written solutions and explanations, and can help you study more effectively and save time. I also offer one-on-one tutoring online. Thanks for watching, and I wish you the best of luck with your studies.